Okay, today we will be discussing about synchronous motors. It is coming under your fourth module, and this is the part 1 of our lecture. And in this lecture, we are giving an introduction for the synchronous motors, about its construction and the principle. Now we know that the motors, it may be a single phase motor or a three phase motor. Three phase motors can be classified, or mainly we can say there are two types of three phase motors. One is induction motor and another one is synchronous motor. So in case of the behavior, it is mainly the difference is in the rotor speed. So in case of induction motors, rotor speed is always less than the synchronous speed. What is synchronous speed? Synchronous speed is a constant speed which is corresponding to the supply frequency, or to get the supply frequency with which speed the rotor has to be rotated. That speed is known as synchronous speed. So whenever the rotor is rotated with a speed which is less than ns, then that motor is known as an induction motor. When the speed of the rotor is equal to ns, then that type of motor is known as synchronous motors. Now here we are discussing about the synchronous motors. I think induction motors are already taken, and firstly we are going for the construction of the synchronous motors. There are two parts mainly. One is stator. Stator is always stationary, and it is carrying the armature winding like in a synchronous generator. There is no difference in that stator part. Stator is stationary and it is carrying the armature winding. We can say the armature winding is the main winding here. Why that term used? Because in case of synchronous generator, the field winding is generating the, first we are giving the DC supply to the field winding, and it is creating the main flux first, phi m. But in case of armature synchronous motor, we are giving the supply, and in that, whenever the supply is given, that flux is firstly created in armature winding. Therefore we can say that armature winding is the main winding, and EMF is induced in the rotor. So it is the main winding, and rotor carry the field winding. Rotor is carrying the field winding. This is rotor actually, rotor. And now rotor. Main field flux induces in the rotor. So main flux, like in a synchronous generator, here also main field flux is induced in the rotor. Now rotor can be designed in two ways. One is salient pole structure and another one is non-salient pole or cylindrical type structure. Now the working of a synchronous motor. We know that this is a motor, so we will be giving an electrical supply, AC supply, three-phase supply. So here there are three windings are there in the stator, corresponding to R, Y and B. So to these three windings we are giving a three-phase AC supply. So this is a three-phase AC supply. This three-phase AC supply is given to a three-phase stator winding, in which each winding is displaced by 120 degree in space, and the three-phase supply is displaced by 120 degree electrically. So if both these are satisfied, we know that a rotating magnetic field will be produced. That you may be studied in case of induction motors about the rotating magnetic field. So I am not discussing about how it is created. Now we know that we discussed like stator is given with the three-phase AC supply, and the rotor is excited with the DC. So we can say this is a doubly excited machine, because to the rotor, since it is a synchronous machine, generally we will be giving DC supply to the field winding in case of a synchronous machine. So it is a synchronous machine. So you are giving a DC supply to the rotor, to the field winding. Along with this is a motor. So we are giving a three-phase AC supply to the stator. So there are two supplies, therefore it is a doubly excited machine. Now stator is given with a three-phase supply and a rotating magnetic field. That is the main term here. Rotating magnetic field is developed. Field having moving polarities is known as the rotating magnetic field. Rotates at a synchronous speed. So when this stator is given with a three-phase AC supply, so what how we can represent that? This is a if we are considering a system, we can consider here. So this is one winding, and here one winding, and here another winding. So the angle between each one of this winding is 120 degree in space. We are arranging like this, and now we are giving a three-phase supply. We usually that three-phase supply will be having an electrical displacement of 120 degree. So if both are satisfied, we know that a north and south in stator a north and south, more than one pair also it may be formed like, but this poles will rotate with a speed, not the stator structure but the poles are rotating. So if this is the stator structure, now these poles are rotating with a speed ns. So there is a variation in the stator field with a synchronous speed. Because of the rotating magnetic field, north and south poles developed in the stator, these poles varying with the synchronous speed. The AC is sinusoidal. Polarity of the wave changes in every half cycle. That is, the wave remains positive in the first half cycle and becomes negative in the second half cycle. Positive and negative half cycle of the wave develops the north and south poles on the stator respectively. Now what about the rotor? Rotor is excited with the DC. DC supply induces north and south poles on the rotor. So stator is external, and inside this there is a rotor, and this rotor is given with a DC supply. When DC supply is given, here a north pole is formed, here a south pole is formed. It will not change. But in case of stator, we are giving a three-phase AC supply, so always that field poles are always varying, but here the field poles are not varying since it is DC. So it remains same. Flux has a fixed polarity. North pole develops on one end of the rotor, and the south pole develops on another end, like this. It will be developed. When the rotor and stator both have the same pole on the same side. Now we know that there is a stator structure. Stator is there. So stator is having north and south. This is rotating with the ns, not the stator but the stator poles are rotating with ns. Inside this there is a north and south, and these north and south are not rotating. These are fixed. This is rotating, but these are fixed. Now what will happen if these are aligned like this? This north pole will repel this north pole, and this rotor starts to rotate. We can consider south here, then it will be more clear. Here south and here north. Now what will happen? This is north and this is rotating with the ns, and the inside the rotor this is stationary, and this north and south pole will attract this north and south. On both sides these poles will attract or repel. Here these are attracting now, and with which speed these poles are rotating, with the same speed rotor starts to rotate. So inside this there is a rotor, and this rotor starts to rotate with the same speed as the stator poles. So now what happened now? This rotor is rotated with a speed ns. So rotor is rotated with. So this is required actually in case of, this is the result actually, because in case of a synchronous motor we have to rotate the rotor with a speed ns. So now the rotor rotated with a speed ns. This attraction is known as magnetic locking between the poles. Now there is an issue. We know that in the stator the poles are varying, not the structure, not the stator structure. But in case of rotor, that rotor structure has to be rotated because it is free to move, free to rotate. It should be rotated. Then only our aim will be satisfied, because rotor structure should have to rotate. But what will happen? Here there is a north, here there is a south. This north and south are rotating with ns, easily rotate. This will easily rotate, but this is a mechanical body. This is a rotor mechanical body. It will be having an inertia. So in case of a synchronous motor, the stator poles are rotating with the speed ns. So this is a stator structure, not the stator structure, but stator poles are rotating. But rotor structure has to be rotated with the same speed. So due to inertia, this is not possible actually. So this is rotating with the speed ns, but this is rotating very slowly, north and south. So when this north is rotating with the speed ns and it will reach here, at the same time this south will be reaching here. In this duration, this rotor is not rotated with the same speed. So what will happen? Earlier there was an attraction between north and south, but now it will be a repulsion between this south and south. So these are repelled. So in the first cycle there is an attractive force, and in the second cycle there is a repulsive force. So both these, so for an entire cycle what will happen? These will cancel each other and the average torque will become 0, and the rotor and the machine and the motor will become it will not be self-started. It will not be self-started. So that is the main issue with the synchronous motor. Synchronous motor will not be self-start. It is not a self-starting motor. So what we have to do for the starting of the machine? So the main reason is due to mechanical inertia of the rotor, it is not able to catch the quick reversal of the rotor, and these things are explained here. And then the synchronous motor is not self-starting. For this we are using some starting methods. So by using the starting methods, what we are doing, the main issue is the inertia of the rotor. So we have to give some rotation. Initially we have to give some force to the rotor, and for that we are using some external methods, some external motors like that. Then it will be rotated after some time. So for that we are using some starting methods which initially rotates the rotor in the same direction as the magnetic field. So with which speed, with in the direction of the stator field rotating, and the same direction rotor is also rotating with the speed which is close to synchronous speed. On achieving the synchronous speed, magnetic locking occurs and the synchronous motor continues to rotate even after removal of external mechanical means. So for that there are mainly two methods. One is motor starting and another one is damper winding starting. Motor starting with an external prime mover. Synchronous motors are mechanically coupled with another motor, and this motor may be an induction motor, a DC shunt motor, or a pony motor. Here we are not applying the DC excitation initially. Now using this motor, the rotor shaft is connected to this motor. So using this motor, rotor is rotated, and when it reached very close to the synchronous speed, we are giving the DC excitation to the field, and now what will happen? This will be magnetically locked with each other, and the external motor is cut off. Pony motor is again a induction motor only, but exactly 2 poles less than the number of poles of the synchronous motor. Now using damper winding also we can start this. Damper winding is like an in case of induction motor, what we are doing, the same thing here also we are doing. That means there is a special structure, special winding structure. In case of a rotor, these are rotor poles, and in the rotor poles we are making some holes here, and we are inserting some windings, and these are short circuited at one end. So rotor is short circuited at one end. This type of structure is seen in case of an induction motor. So like an induction motor, it is started like an induction motor. So synchronous motor with the damper winding is started like an induction motor. So induction motor will be rotating with a speed less than the synchronous speed, but very near to synchronous speed. Here also this is started like an induction motor, and it is rotating with a speed which is less than synchronous speed but very near to synchronous speed. So when the synchronous speed is reached, then that induction motor action will not be there, and it is locked with the field poles, stator poles, and it starts rotating the ns. So it is usually it will be synchronous motor is of salient pole structure, because the damper winding is mainly we are employing in case of salient pole type machine, and relative that there should be a relative speed actually. That means it should be less than ns. That the speed of the rotor should be less than ns. Then only this will happen. So this is the case of this damper winding starting. So this is again the main features of the synchronous motor. Synchronous motor are inherently not self-starting. We are giving some external means for the starting. But when it is started, it will be rotating with always with a constant speed and constant frequency, irrespective of the load condition. In case of induction motors and all, there may be some changes with the load, but here there is no change. It is always rotating with a synchronous speed. And the another main advantage of this motor, it can be operated at under any electrical power factor. This is not possible in induction motor. Induction motors are always operated with a power factor, lagging power factor. But in synchronous motor, both leading and lagging power factor may be possible. Why it is possible? Because there is a DC excitation. By controlling the excitation, we can control the power factor. So that is the main attraction of the synchronous motor. So with this, we are stopping here, and we'll be continuing in the next class. Thank you.